Okay, so usually when the presentations, the technical presentations, this workshop, we start with the ScaLAPAC because it's intended for calculations, computations with dense matrices, and also because the tools that will follow are they're more they provide more functionalities than the ScaLAPAC, I would say. But even if you are, so as I said, this is intended for dense matrices, but even if you are dealing with sparse matrices, in some cases, depending on the techniques that you are using, you may finish with some dense blocks. One of our colleagues there mentioned mumps, and it seems to me that that's the case with mumps, right? At some point you use or used to employ ScaLAPAC for a dense block there.
We would like to have a DLT instead.
Okay. So so what is a ScaLAPAC about then? In this presentation, I'm going to tell you about the functionalities and some of the applications that have benefited from it. I'll talk a little bit about the data, the software structure, and some details about the data layout, descriptors, and some examples, or rather the hands-on that we'll have later today. So this is the idea here. In those 4 bullets, you can have an overview of the kind of problems you can solve with a ScaLAPAC. Linear systems of equations of the type AX equals B, in some cases with more than one B, in other words, multiple right-hand sides. You can compute singular value decompositions, SVD, right? The product, you take a matrix A and write it as a product of 3 matrices. Two orthogonal in the real case, 2 orthogonal matrices U and V, and 1 diagonal matrix sigma, which contains the singular values. You can solve least square problems of that kind, mean of AX minus B, and the true norm. And you can also compute eigenvalues and vectors. For the standard eigenvalue problem, A is equal to lambda Z, or the generalized eigenvalue problem, A is equal lambda B Z. And what this table shows, although we're not going to go into the details of the table, you have it in your copy of the slides, but it basically tells you the different ways you can solve the linear systems or compute singular values or eigenvalues. There are different ways, in a kind of more simple way of computing things or a more kind of expert way of computing things, and that's what the table shows. And also, one thing that our ScaLAPAC doesn't have, it doesn't have a storage scheme for more kind of specialized data structures. It's intended as, it's important to remember, dense calculations, but in some cases, there are also functionalities for triangular matrices or banded, and that's what we have there. For symmetric and also non-symmetric matrices, okay? So some applications that have employed functionalities available in a ScaLAPAC. The one in the top left there, it's an application in physics. It's basically, this is an applications in material sciences where people are interested in computing energy levels. And what you can see there is basically a charge density for a glycine molecule. And this basically, in this kind of application, usually you finished by having a dense, complex, or Hermitian eigenvalue problem that people have used the ScaLAPAC to compute eigenvalues, which in this case are basically energy levels. The one in the top right is basically, it's a model that I was at the time collaborating with some of my colleagues here at the lab, a geophysicist, and he was developing a model for the internal structure of the Earth using sound waves generated by earthquakes to validate the model. And in this case, there is a singular value decomposition problem that he was interested in, or he had to solve, and I helped him with using a ScaLAPAC. So the one in the bottom left is an application that there in Oak Ridge, related, I think, let's see here, I think it was plasma physics. And there is this AORSA code that they basically had to solve a complex system of linear equations. And the one in the bottom right is an application in astrophysics that I would say in the past, with this application, the astrophysicists could show, the results showed that the universe is expanding. And the curvature of the universe is flat, meaning that the universe is expanding. And in the last several years, there were basically 2 Nobel prizes here at the lab that were related to this research. And basically what happened here, they took pictures from the sky. Okay, so actually that's a picture, but the picture there is actually for it's the temperature, it's the residual temperature, just I think it's, if I remember, some of my colleagues may correct me, 200,000 years after the Big Bang. Okay, so then they took measured the temperature, and by doing some data analysis of that information, which basically requires solution of a linear system of equations, okay, in their formulation, they could show that the universe is expanded. The experiment is Boomerang. It's called Boomerang, or part of the experiment was called Boomerang, and that made the cover of Nature. You can see there is a balloon there, and this balloon, as I said, the experiment was called Boomerang because the balloon was launched in the South Pole during a certain period of time of the year. And if you launch the balloon at a certain point there in the South Pole, the balloon comes back to the same point because of the winds. So that makes things easier for the astrophysicists to retrieve the instruments from the balloon and read the information that's in there. Okay? And you cannot see, the resolution here is not very good in this picture, but there are 3 somewhere there. Perhaps if you make your PDF file bigger, you can see 3 dots, 3 white dots in that picture. Those are 3 quasars that are very far away in the universe that finished by showing up in this picture. But anyway, so the message here is this: there was some data analysis being done there, linear systems of equations. They were using ScaLAPAC to do it. Okay, so this is the structure here that we have in the software. There's a number of layers that ScaLAPAC is built upon. So if you go to the web, there is a Doxygen page now there in the top right corner that if you can see the structure of the package in more details. And then we're going to go quickly here through each one of these layers just to give you a flavor of how these libraries, are built. So there is one, the one in green there, that's basically the communication layer. These days we used mostly MPI. In the past we could, or I think there are some people, if you have a network of workstations, you could even have PVM, for those of you who have ever heard what it is, but a parallel virtual machine. You could build ScaLAPAC using PVM. There is a layer that's the BLAS, that's intended for some basic matrix linear algebra calculations. We'll see what it is if you're not familiar. There is the parallel version of the BLAS. Those are the PBLAS. And in between the communication layer and the PBLAS, we need something to help us with the specifics of linear algebra. And then we have LAPACK. That's a linear. It's a package for linear algebra calculations, but sequential. And also we can use some of those sequential calculations in ScaLAPAC as well. So as I said, we're going to go quickly through this. So the first one that you may have heard is the BLAS, right? The basic linear algebra subroutines that are basically defined in 3 levels. Level 1 for vector-vector calculations, vector 2 for matrix-vector calculations, vector 3 for matrix-matrix calculations. And all other libraries, numerical libraries that we'll see during the workshop use this BLAS somehow underneath. Just to give you an idea of performance, so in this picture here, or in this graph, what we have is the performance you can get for operations of the kind of vector-vector in blue, for matrix-vector in green, and for matrix-matrix in red. So for various matrix sizes which are in the x-axis, and the performances there are given in megaflops per second in the y-axis. And you can basically, the message from this picture, from this graph is this. If you can use BLAS3 as much as possible in your algorithms, you can basically achieve performance almost for free. right? And these calculations were done in my workstation up at the lab. It's an Intel. It's not even the latest model, a Xeon E5630, using the ASM, the AMD library. So then what happened is that over the years, people have been rewriting their algorithms, if possible, using BLAS 3, right? If you can rewrite your algorithm using matrix calculations instead of matrix vector, that's a way to, as I said, to have performance basically for free. Okay, and this is what have been done in in LAPACK and also ScaLAPACK. I mentioned LAPACK. Basically, it's a library written in Fortran, but it's widely used. It's built on top of the BLAS 1, 2, and 3 routines that I mentioned to you. You can solve linear systems. You can solve least square problems. You can do singular value decomposition and also solve eigenvalue problems, similar to what a ScaLAPACK provides. But here it's sequential. LAPACK does not provide routines for particular kind of data storage. For those of you who are familiar with finite elements, it doesn't have things for dealing with, say, skyline storage or for sparse compressed row. It's basically either dense or banded. Okay. I don't know if it's still the case, but there was this, someone had the curiosity, when you download or when you install a Linux package, Linux distribution, LAPACK usually comes with the distribution these days, and someone had the curiosity to count the number of lines of codes in the distribution, and surprisingly, Fortran came in second because of LAPACK coming with the Linux distribution. The first one was C, of course, but the second was Fortran in the distribution because of LAPACK. Let's talk about the BLACS, which are the basic linear algebra communication routines. Okay, so this is a layer built on top of MPI or the parallel protocol that you want to try or to port the BLACS to, which is basically facilitates the communication for arrays. That's the idea. If you're going to transfer data using MPI, arrays, you may have to do perhaps write a few lines of code, depending on the kind of array that you want to send or receive. With the BLACS, you basically have one line of code that can do that for you, and all the things that are needed by MPI are underneath. So that's the idea. It's intended for portability and also to make it easy to write codes, easier to write codes. And in what concerns the parallel usage here of this, the BLACS, okay, and of course we are talking about parallel computations here. Everything has to be defined in the two-dimensional array of processes or cores these days. So in the past, it used to be one core or one node, one core, right? These days, we have one node and lots of cores. For example, the Cray we have. At the lab, we have 24 cores on a node, right? So in the past was one node, one core, as I said. But here, just to give you an idea, we have 12 processes or 12 cores, and we distribute in a 3x4 grid, okay? So we have 4 processes on 4 rows of processes and 3 rows of processes and 4 columns of processes in this case. We start counting from 0, like in C. And for the columns and also for the rows, and if we count the processes also starting from 0 and row-wise, following the C way here, 0, 1, 2, 3, 4, 5, 6, 7, and so forth. Okay, and given a process and a column row, of course, we can identify the rank, say, of the process or the core, participating in that particular grid. Where we have to distribute our data on. And there are different ways we can process the information once we have defined a grid. We can have only the processes on a row participating in a certain calculation, only the processes on a column doing some calculations, or all of them. And so that's the meaning of that table in blue, we can have the scope of the calculations or the data distribution defined by row, column, or all. Okay, so that's how things work in the BLACS, and similarly for the calculations that are done by ScaLAPAC. There are a number, as I mentioned to you, the BLACS is basically a layer of functions that can help you, to deal with linear algebra data in an easier way. And instead, for example, of calling directly MPI function to send and receive data, you can have at the top of this slide that BLACS function that's called SD2D, in other words, send data in 2D, right, or in a 2D dimensional grid. The red, the underscore there in red, could be replaced in the actual function by an S, D, C, or Z, meaning integer, real, double precision, complex, or double precision for that particular function. The two x's there in green would be replaced by GE, meaning I am sending data related to a general rectangular matrix, or TR, I'm sending or receiving data related to a trapezoidal matrix, right? And there is a function for broadcasting data, similar to the ones at the top, where I can, again, the underscore for integer, real, double, etc. The two x's for general or trapezoidal. And the scope, as I mentioned before, could be data, being transferred or broadcast in a row, in a column, or all. And if you have more information about the topology of your computer, of your parallel machine, you could use that in that entry top in order to improve performance. If you don't say anything, it's just the BLACS are going to try to, when you install, the BLACS are going to try to figure that out, and you don't have to bother, with the topology. Only if you really want to play with the topology of your computer. This is an example. If you have questions, please feel free to interrupt me at any time. So this is a very, yes, right there, one. The other previous slide?
2 slides. Yeah, this one.
Yeah.
So what does that number represent? Like 0, 1, 2, 3?
It's equivalent. I guess you're familiar with MPI, aren't you? So it's basically, that gives you, that's the, you have 12 processes in this example. It identifies each one of the processes. So it's a unique way of identifying. Yes, it's equivalent to what we say a rank or a task in MPI. Okay. Any further any questions? Other questions here at this point? Now let's go through this example. It's just a piece of code, very simple for run here. If you are familiar with the C or any other language, it would be basically the same thing, because you can use BLACS in the same way. And again, it's very similar to MPI here. The way we start things is by a call like this. In MPI, we would say call MPI rank or something like that. Here we would say BLACS info, by basically getting information about the grid. And when I have this call here, I get the number of processes, or number of, in that particular example, 12. That's what would give me back here. Okay, and any prox would be 12. IM, the first argument there would be 0 to 12, 11, depending on the coordinate of that particular process. So that's how we get some information. Going next to here, we have to initialize things, right? We can get we get here what we call a handle, which is basically a communicator in the MPI jargon. That's equivalent, okay? And going on here, as I just said that, it's basically it's a way, the context a way for, it's a mechanism to partition your communication space. In one application, you could have, for example, you could define, say, 32 nodes, or rather cores. And you could say, well, I want 16 cores working on a certain data, and the 16 remaining cores working on a different data. Okay, but doing, say, solving a system of linear equations, but just with a different right-hand side, say. You could do that by specifying two different contexts or two different communicators in MPI. You could then separate the space that you are going to do your calculations on, and they don't talk to each other. They're basically isolated from each other. So that's the idea here of the context. So then the context allows you to create an arbitrary group of processes. And depending on your application, you could play with this mechanism in order to, better deal with your data and your calculations. Then you have to, basically, what you can do is to get the coordinates of that processes that you may want to use, for example, next to send and receive data around. That's what happened in there. I'm basically saying, well, that piece of code, if I am in row 0 and my column is equal to 0, then I'm going to send data to the other process that's in my row equal to 1 and my column equal to 0. That's basically what that if statement, if the two branches there are doing. Just sending data to a specific process in that grid. And then the process that's supposed to receive that is indicated there in the second branch of the if. Right? So if you get the coordinates of a particular process, you can do, the kind of sending data that you want. In general applications, usually everybody or all processes participate in the calculations. But here, it's just, again, to show you how you can separate things. And at the end, you have to leave that particular, group of processes, and you exit. It's very similar to MPI. But again, it's done this way just to make things easier, to pass arrays around or matrices. Now, with that in mind, we have the parallel version of the BLAS, right? Remember, vector, vector, matrix, vector, matrix, matrix. We have a parallel implementation of those calculations. The call is very similar to what you would do in sequential way, okay? With the exception that there is a P here added at the first character to mean, and that means parallel, okay? And what is interesting is that suppose you have a big array that's indicated here in green. Okay, you have an array of dimension m underscore n underscore, but you want to perform calculations only on that piece of the array indicated in blue with dimension m and n. And then you have this layout, this offset rather, starting at the row IA and column JI. Okay, so that's you want to do, for some reason you want to do calculations only on that piece in blue. How do you do that in parallel, right? I mean, you have to distribute this data, but tell all the processes involved, this is where my data is. I have the big data, but I want to work only that piece. So you need to pass some information to the function to say, well, this is where my data starts, and this is where I want to perform my calculations on. The way we do this is by defining what we call an array descriptor, and we'll see what an array descriptor looks like in the coming slides. It's basically, so the idea of doing this is because in order to have performance, it used to be the case in the past that Fortran used to give better performance than C, right? I think these days the performance of codes written in Fortran and C are and even C++ are very comparable. But then in Fortran, we don't have those, although in Fortran 19 now it's Fortran 95 is a little bit better, we don't have the notion of objects, right? Where you can basically, you can define a construct, say, or a derived data type, and pass all the information in a single, in a single entity, say. So the way to pass more information that is needed for calculations in parallel in a Fortran program is through an integer array. So that's basically what the limitation here, and we'll see what descriptor looks like in the coming slides. Now we get into ScaLAPACK itself. It's basically then a library built on top of those layers that basically use BLAS 3 matrix vector, matrix calculations as much as possible in order to have a good node performance. It's reliable because it employs algorithms that are available in LAPACK and have been tested in a number of computer platforms using lots of different compilers. It's scalable, perhaps not to the kind of machines that we have these days with 150,000 cores or more even, right? There, how many cores we have in Sequoia now? 300,000. There is already a machine here in Livermore with 300,000 cores, perhaps. And Mira in Argonne, how many? 750,000 cores in the IBM they have at Argonne. Perhaps you are not going to use ScaLAPACK at that level because that would be a very big dense matrix, right? But in smaller scales, a fewer or less cores than that, ScaLAPACK scales reasonably well. It's portable. And it's not that complicated to use and once you get, to understand it a little. What are the parallel distributions that are possible with ScaLAPACK? You can, for example, take a matrix. Let's not thinking in terms of the scale of this picture. Suppose you have only 4 columns in a matrix, right, like this. You can distribute your data, assuming you have 4 cores, like this. Core 0 takes this column, core 1 takes this, and so forth. If you have more columns, in this case, you would have 1, 2, 3, 4, 5, 6, I think. 6 times 4, 24 columns, I think. You could distribute the columns like this, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and so forth. And we call that one-dimensional column cyclic distribution. Okay? We could take more than one column and do the same thing, 0, 1, 2, 3, 4, assuming that in each one of these guys here we have more than one column. We call that 1D block column distribution. And we could do this by rows as well. And if we do that by rows, then we have what we call a 2-dimensional block cyclic distribution for our data. And the question that you might want to ask now is, why do we have to go through this kind of difficult data distribution? By doing this kind of a cyclic distribution, you can have a very good balance in terms of communication and computations. So there is a whole theory behind this kind of 2-dimensional cyclic data distribution. Sorry? For dense linear algebra. But actually, even if you are using super LU, that's a sparse, a solver intended for sparse matrices, although you don't see it, you just provide your data to super LU in a compressed sparse row format. Super LU does some rearrangement of your data behind the scenes and puts the data in this format. In blocks, in dense blocks, but it still does the 2D the block cyclic distribution. One thing that I'd like to mention is that although ScaLAPACK does, you have to do this when you are using ScaLAPACK. There is a tool that's global arrays that you can use to, right, Bruce? You can do a 2D, it can global arrays that Bruce is going to talk about later after the break. Can be used to do this data distribution that's required by ScaLAPACK for you. This is an example of how things work here for this 2D block cyclic distribution. You have, in this example, you have a 5x5 matrix partitioned in 2x2 blocks, right? So there is the dotted lines indicate the partitioning of that array in 2x2 blocks. Suppose we want to, I just changed the colors. It's the same entries, right? The same matrix. I just changed the colors to make things easier to see in what is going to happen next. Suppose we want to distribute this data, this small matrix, into 4 cores or processes using a 2x2 process grid. So this is how things work here. Basically, using that notion of a cyclic distribution, we start with this one in red. This comes to process 0. We skip this because it's cyclic. We come to the yellow. The yellow also goes here to 0. This is by columns. We do this by rows. This one has already been placed. So then we have to skip this because it's cyclic. We take this one that's kind of brown, and this is where it comes. Okay. The yellow is already there. We skip this one, and then we take just one entry, and that's where it comes. Okay. What about this part? Well, it comes to the next. It goes to the next process. It goes to 1. And if we jump this block, we take this. It comes to 1 also. And we repeat this, this process to distribute the data for the green, for this piece here, and for this one in sort of magenta, I think. Okay, so that's the idea of the 2D block cyclic distribution. You take your array, you partition it in blocks, in this case 2 by 2, and then you distribute among the number of cores that processes you have in this way. And it may be the case that when you partition the array, you have one block with one entry. There's no problem at all with that. Why do we have to partition an array in blocks? Well, I already said if we do if we use this idea of 2D block distribution, it's good for balancing communication in the calculations in dense linear algebra. Why to do this blocking thing? Because here you can use BLAS 3 in most cases in a very nice way. Okay, so that's the notion behind the blocking here. Questions? I can go back and repeat if necessary, or we just, in this case, in this slide, we see how we would code the data distribution. If we take, again, that matrix from the previous slide, this is a very simple piece of code showing how the data, for example, if I am in row 0 and column 0, if I am in that process, this is the piece of the array that I'm going to get. So that's basically what is happening there. And the same for the other 3. But now, what is happening here is that although this array it's a 2-dimensional array, I'm storing the array in a vector-wise. Why? Because it's easier this is easier, for example, if we're doing, working in putting together C and Fortran programs. Since Fortran works by columns and C works by rows, if you define things in a one-dimensional array, this works for both. Okay, so it's fine with Fortran and C, and you don't have to be worried about messing things up. Another thing that's interesting here by storing a 2D array into a vector is that you may have your big array embedded. You have the array, actually, that you are interested embedded in a bigger array. And then by using the notion of leading dimension of A, you can very nicely define only the piece that you are interested in one-dimensional array. So that's another benefit, another interesting feature of mapping a 2D array into a one-dimensional array. Okay, and that's what is happening there. I'm defining in each one of the processes the data that should go there, and then I call, of course, in this case, it's a function to compute a singular value decomposition. In real applications, you are not going to do basically for this example, I hard-coded the matrix. In the real applications, you're not going to do that. There are better ways that you can, you can take information about your application that you can map nicely into the data distribution that's needed in ScaLAPAC instead of hard coding like this. Okay, this is just for the sake of the argument here. And this, it shows up again here, the array descriptor, which is that, as I mentioned before, it contains information about how the data has been distributed. It's information related to the mapping between your big array, right, your global array or matrix, and how it has been distributed among the cores or processes, okay? And that's what the descriptor array looks like for dense matrices. It's an integer array with 9 entries. Each one of those entries, tells you or contains information. For example, this is the context. This would be the MPI communicator, right? So the number of rows in the global array, number of columns in the big global array, and the other information for the local arrays. We'll see in an example, more about this in the hands-on. So this is array descriptor for dense matrices. Basically, you don't need to, pay much attention to the details here because you'll see how it works in an example this afternoon. There is also an array descriptor for narrow-band matrices, and similarly, it's a mechanism to pass information about how your band matrix, for example, tridiagonal matrix or a pentadiagonal matrix, has been distributed, okay? And the third kind of array descriptor is intended for right-hand sides when you are solving a system of linear equations. Right-hand sides have to be dealt with in a slightly different way, and we'll see again in the hands-on why. So if you are writing codes using ScaLAPAC, and eventually you are going to run into an error, the best way to, you have to, of course, to check your input, and in some cases ScaLAPAC can give you some, there is some checking that ScaLAPAC does behind the scenes. And if the data that you are passing, they don't or satisfy certain requirements, it gives you an error message that you can then, of course, use to debug. Or you could also use take a look at the examples, right, that come with the package to see what is eventually wrong with your code. That's basically what I have here. There is a way to, so when this was implemented, it was used still, ScaLAPAC was implemented. It still used static arrays and not dynamic allocation of memory. But there is a way that you can invoke ScaLAPAC and figure out how much memory you need, and then you can allocate the memory and call ScaLAPAC. So that's a way then to figure out, and use memory in a better way instead of just allocating a big chunk of memory and perhaps not use all that memory. In terms of performance, what you don't want to do is to, if you have an application, what you don't want to do is to distribute your data and try to solve your problem using lots of cores or lots of processes with very small matrices, okay, distributed among these cores or processes. The rule of thumb is that you are going to split your application or your matrix in a way that the smaller pieces are basically of the kind of dimension 1,000 by 1,000. With these small pieces or submatrices of dimension 1,000 by 1,000, you can basically use BLAS 3 and there are other things there that are you can benefit from. Also, with this data distribution, in the example I showed, the small 5 by 5 matrix, I used a partition of 2 by 2 blocks, right? Actually, for the hardware that we have these days, it's basically to have a better use of cache memory. If you use a block size of 64 and even bigger, 128, that would be much better. We would get much better performance than 2 by 2 blocks, okay? So then the message is don't use, when you're solving problems in parallel with ScaLAPAC, try not to have small submatrices, right? Because you're going to pay a price there. And that's basically the costs for communication are likely to dominate the costs for the calculations. This is an example here of just to illustrate what the performance of ScaLAPAC could look like. What I'm doing here is doing an LU decomposition, taking a matrix A of various sizes, which are indicated in the x-axis, sizes from 3,000 to 23,000 in x. What I'm doing here is decomposing this matrix as a product of a lower triangular matrix L, upper triangular matrix U, and I'm solving the system of equations, system of linear equations with those factors using a block size of 8, not 64, 8 in this example. And then the y-axis, you have the time that's needed for that, and starting from 0 to 120 seconds in that case. And what these bars have, the different colors in the bars, that's for number of processes for, from 2 to 64 processes, or cores in this case. And this is on Carver, the machine that we're going to use this afternoon and the coming days for the hands-on. And we basically, what we can take a look here is at the matrix of dimension, just for this, to illustrate. Dimension 13,000. You see that if you use only 2 cores, it takes 120 seconds, almost 120 seconds. If you use 4 cores, the time it takes is basically half. Just to give you an idea of how fast the kind of improvement that you can get. But as you increase the number of cores, for example, from 32 to 64, that's what we have here, don't expect to have the time divided by 2, right? Because you would need a matrix bigger than that. So you get to a point, as I mentioned before, that the size of the submatrices in each one of the blocks, you cannot get performance. Basically, there is a trade-off between the size of the submatrices and the communications that need to be done. And that's basically what we can see in a plot like this. You will still get a good performance if up to, what's this color? 16. Actually, up to 32. But then, things start flattening, becoming flat. That's the message here. Another interesting thing is, and in this picture, again on Carver, for that same problem of the previous slide, although here I'm just using problem sizes from dimension 1,000 to 12,000. I don't go in this particular plot to 23,000. Again, NB equal 8 is the blocking of the matrices. I am using 60 cores always here. Okay, but what I'm doing is distributing the data in different ways. I said, well, we have the 2D distribution, okay, but we have to define a 2-dimensional grid. But what I have done here, I have used the 6x10 grid, 5x12, 4x15, 3x20, and 2x30. Always 60, but in distributing a different way. And look at what happens here with the performance. We can focus, for example, on the dimension of 12,000, which is the last one. If I use a grid of dimension 6x10, the time is up, it's 90 seconds. Okay? If I use a grid of 2x30, let's see, this is 1, 2, 3, 4. That would be 1, 2, 3, 4. It's between 5 and 6 seconds. Another thing that's important to remember then, it's not only the distribution of your data in parallel, but how you distribute it, okay? So how you define your grid. For this particular LU plus solve, the one that gave us the best performance on this architecture was 2x30. It's not always the case. It depends if you are solving an eigenvalue problem or an SVD, this situation, or this kind of plot here might look different. Okay, so then there are 2 things: the data distribution and how you distribute it. So this would be impact the performance. And this is not only, it's true for ScaLAPAC, but also for other libraries. Okay, depending on how you distribute your data, you may get different performances. Okay, so ScaLAPAC has been used by a number of different packages. For example, if you buy a Cray machine, it comes with the libsci library provided by Cray. If you buy an IBM machine, it comes in the parallel version of ESSL and others, right? It used to be, I don't know what happened with the Sun Scientific Library, but at some point, Sun, that was bought by Oracle, it's used it. And the Japanese Fujitsu and others, they have libraries, and ScaLAPAC comes with it. Lots of people have worked on the project over the years. You can see the list there, and there are more that I may have forgotten. Here I have to mention some projects that are related to ScaLAPAC, and depending on your application, they could give you better performance. I think it's fair to say that ScaLAPAC gives a very range of functionalities for linear algebra calculations. But there are other, newer developments, like, say, PlayPack, they're in Texas, that also could be used for solving systems of linear equations or eigenvalue problems, depending on the kind of problem you have. There are Magma and Plasma developed there in Tennessee, University of Tennessee, Knoxville. One of them intended for GPUs and multi-core architectures, and the other one also. But the distinction here is the GPU between the two. They are still in development, so that's the reason here. Let's see, that I used two. One is more mature, which is PlayPack. That's the black bullet. The other ones in red are still under development. So this is the website where there are some hands-on. So there are some exercises, and we are going to go through these. Not all of them, but we're going to focus on one of them this afternoon. And I'm going to show you, there is an example how the data is distributed, and how to run it in parallel this afternoon. This is what they are. So there is basically a very simple program, hello world, and there's an example using pi. It does a numerical integration of a formula to compute the value of pi. And there are a number of examples. As I mentioned, we can go through them all this afternoon. This is more examples here. There is a tridiagonal matrix that will be, if we have time this afternoon, also we'll solve the tridiagonal with two different right-hand sides, and we'll see how to partition our grid to do that. And also, there is a, I'd like to show you later today how there is a script that we have put together that, you can, it's for training purposes. Given a matrix, the number of cores or processes and the grid distribution, what the data distribution should look like. And by getting familiar with kind of data distribution, you could then, if you have an application code, implement that kind of distribution to your code. Okay, so we'll take a look at that this afternoon. I'll just skip this because I'll come back to this. And then the final slide in the presentation. This is basically instructions for getting the hands-on this afternoon, uncompressing things and compiling and running on Carver this afternoon. But then again, so I'll come back to this last 3 or 4 slides this afternoon to refresh a little. With that, if you have any questions, I would be glad to go back and repeat. Yes, sir.
So you said the MPI task distributed in this 2-dimensional grid sort of thing. What is the purpose of that? That I didn't catch. So when you use that blocks, BLACS?
BLACS?
Yeah. So it distributes all of your tasks in a 2D array instead of...
What is the purpose of the Block-Cyclic?
The purpose of the Block-Cyclic is to have a good balance between communication and calculations. If that was the question.
Like I saw that you had the 2 by 30 versus
Let's go-
3 by
Let's go back
20
there.
versus whatever. I don't know why that affects the performance. I guess. I don't know how that's...
Let's see.
integrated with the rest of it.
Is this one here that you mentioned or before?
Yeah, that one, for instance. So, I mean, you do the same problem size. The MB was, so each of the small blocks was 8 by 8,
Yes.
and then you do it with the Block-Cyclic 2D version or whatever, and so it goes to each of the ones. But I don't understand how the grid shape itself.
The grid shape plays a role in the distribution of the data as well. And it's, so if you take a matrix and okay. Okay.
So like, if each machine has 6 cores and there are 10 machines or something, how does
Okay.
this...
Okay. So let's go here. Let's go here. This is, although this is of course on a much smaller scale, what is happening in that example is something like this. You have a block, in this case with 9 entries, and you have a block with 4 entries. This kind of problems with balance that you have in that big example, that you have that curve that with different performance. In other words, when you are dealing with this block here, you have a lot of you have more calculations being done on this block than on this block. And also, you have different requirements for sending data around in the parallel. That's what you see in that in that plot, but in a more kind of a dramatic way. So ideally,
Is there a rule of thumb for picking this?
blocks of similar size or sub-blocks of similar size. It depends also on the algorithm. Yeah.
Okay.
So for example, the algorithm there, that is used for the LU decomposition may have different properties than if you are going to do a singular value decomposition, for example. But this, with a few tests, you can figure out what to do.
But also, so I think you asked 2 questions. One was that about the load balancing. But imagine if you had used one of the other approaches that Osni showed, like let's say you partition by rows of columns, blocks of columns, or blocks of rows.
Yeah.
You ended up having that some processes are going to have more communication than others.
This.
And also because of the pivoting, that some of these algorithms use, you really don't know which part of the matrix is going to require a lot more, where the computations are. By distributing pieces to everybody, then you sort of automatically load balance. And sort of, in this particular case that OSNI has, it looks unbalanced. But in terms of, actual computations, maybe.
Is it clear or not?
As clear as it will be for the moment.
Right. But another thing.
That's good.
I think that is is problem independent. What we have seen in the especially for multi-cores, is that you're going to see that this blocking that Osni is talking about is we just have something empirically, but we don't know fully. It's like we can give you a formula that you can go and apply to your particular blocks.
So you see what happens when people are writing simulation codes and they move to one platform to another. So there are some runs that are done, right, to see if
To calibrate.
to calibrate. For example, you may remember that application astrophysics, this one here.
I remember there were 4.
Okay.
Ah, yes, there were 3 white dots. Yeah.
Let's see if I get it here. I think this is the one. So for that application astrophysics, the development of the data analysis code started on a Cray. Okay, so they were using certain a sequence of calculations to do the computations that to solve the problem they need. When they ported, and they were getting very good performance. When they moved the code to another computer, in that case it was an IBM, the performance was very poor for the algorithms that they were using. So they had to then just to change 2 lines of code to change basically the order of the calculations in order to make the application perform well again. So basically that's what you have to do. Some sort of validation or calibration, as Tony said. And the same applies here for the blocking and for the data distribution. It may vary from one architecture to another. Because then you have the topology of the network,
Yeah.
Yeah.
If I can also add, is that one of the things with multi-core, what we have seen is that, let's say we have a 24-core on Hopper, but let's say our application all of a sudden, the person that puts that problem is a problem that's dominated by other areas than your solver. Well, this is ScaLAPAC. So then you cannot really use the 24 cores, but you can only use 6 of those cores. And really for MPI, you don't have a way to tag each core, which core, select those cores. So that blocking is an issue. Can be but you selected thinking that you had the 24 cores, you may need to do something different for the 6. And that's where I mentioned, the auto-tuning stuff, is having those parameters that'll help you, drive that. So let's thank Osni and